Hey everyone, it's Stoltz. I know you might remember me from such things as being your math teacher for ninth grade extended. Unfortunately, I'm at school, but I'm not in class today. So rather than just have you work on worksheets or something like that, I figured I would teach you a lesson. I would just do so virtually. So here we go. Today we are going to look at a concept that we've already kind of seen and played around with. Um, and it is finding the domain and to some extent the range of a function. We're really going to focus on the domain today. Um, but realistically, there are three different ways that we can find or the things that limit the domain of a function. The first thing is something we've seen already, and that is the idea of the graph of the function. Just so you're aware, right up here, you can see I have given you the these are the must-dos that we're doing this week or for this lesson. So you've got all of that available to you. You can also check the notes that are on Google Classroom. All of that's available to you. But let's just jump right in and let's look at the first thing, the thing that we most common deal with when we are looking at the domain of a function. So the first limit is the graph. So the first thing we look at is we're looking for maxes and minimums. And then we're also any holes in the graph. So that's what we're looking for. So if I look at this graph that I have put there, you can see it looks like a parabola. It goes off the screen because it goes on forever. However, it does have a hole. We've got a limit right there. So if I was going to write down the domain of this particular function, I would say x such that x is greater than negative 15 and x is an element of the real numbers. So again, we use strictly greater than because the dot has a hole in it. So it means that it goes right up to negative 15, but it never actually is negative 15. So it's like negative 14.9999999, but it won't actually ever hit 15, or that negative 15. If we were going to look at the domain of this function, or if we we're going to look at the range, we'd need a little bit more information. We'd have to have some information about what this minimum spot actually is, because my range is going to be y has to be greater than or equal to that. Not super worried about that right now, just kind of focusing in again on one of the concepts. So three different ways of limiting domain. First off is if the graph of the function has it, then that we got to look towards that. The second way that we can do this is dividing by zero. We are still not allowed to divide by zero. So if we ever have a function, something like f of x equals 1 over x, then anytime the denominator of a fraction becomes zero, we can't have that. So that limits our domain. So if the denominator of a fraction becomes zero, that is a limit to the domain. So in general, the way that we find it is we just set the denominator equal to zero and then solve for x. So in this case, if I set x equals zero, then the rule is x can't be 0, so my domain becomes x such that x is not allowed to be 0, but x is definitely a real number. Okay? That's pretty basic, pretty straightforward. Let's look at something that's maybe a little bit more complicated. Something that is more complicated in this case would be something like if g of x was equal to 2 divided by 3x minus 1. Okay? So we're going to follow that exact same thing we did before. We are going to set the denominator equal to 0. And then we're going to solve for x. So we're going to set it equal to 0, then we're going to isolate x, and that will be the limit, the thing that we cannot have. So if I do that, so I do 3x minus 1 is 0. That would give me 3x is 1, because I'd add 1 to both sides. And then x is equal to 1/3. So that denominator becomes 0 if x is 1/3. That means that x cannot be 1/3. So the domain, once we solve that, once we have what makes it go to 0, then we set up our domain saying that it can't be what makes it equal to 0. And that is kind of like, that's pretty straightforward and simple. I kind of like that. And by the way, just I think that it might be a worthwhile thing for us to see it. If I take and I graph that function, so it was 2 divided by the 3x minus 1. And this is what that function ends up looking like. This is called a rectangular hyperbola. And what we can see if we do menu trace and I do a graph trace, if you'll see that right here it's fine. If I press space and then I do 1 divided by 3, it doesn't show up. It doesn't have a value because it's not allowed to be that. Our x value is not allowed to be 1/3, and that's what that is showing us. That's this asymptotic behavior. So, first rule is about graphing. If the graph has a limit on it, that's our limit to domain. Second rule is if there is a variable in the denominator of a fraction, we have to solve because it can never, ever, ever, that we can never have 0 in the denominator of a fraction. So that's our first rule for algebraic. So we got graphing, we got algebraic. We've got one more rule. And this other rule that we have to be able to do is if we ever take a square root of a negative number. Remember, the square root is asking us what number times itself equals the radicand. And the radicand is, again, just the value underneath the radix. Well, there is no way of me multiplying a number by itself. It can never, ever, ever be less than 0. That's just not possible. If I square a number, it will always be positive. So, if I have the square root of a negative number, I'm in trouble. I'm not allowed to do that. So the other way that we can limit our domain is if we have something like h of x equals, let's say, 2, and we do x minus 3. Well, what we need to do is we need to figure out what happens if this gets below 0. So this value here must always has to be greater than or equal to 0. Because we can take the square root of 0. The square root of 0 is 0. But as soon as we dip below 0, we're in trouble. So for this, we're just going to set the radicand, the value underneath the radix, greater than or equal to 0. Because it has to be greater than or equal to 0. And then we're going to solve for x. Okay, so very similar to if we have a variable in the denominator of a fraction, we just set the radicand. X minus 3 has to be greater than or equal to 0, and then we just follow our rules for inequalities. So this would be x has to be greater than or equal to 3. So my domain for this function, x, such that x is greater than or equal to 3, and x is an element of the reals. Okay? So just like with the fraction, we set the denominator equal to 0. Here we set the radicand equal to or greater than 0, and then we solve. Graphically, we can see that as well. If I tab and I do, control square root of, what was it? X minus 3, you can see that this graph starts at 3, 0, and it goes off to the side, and it's going to go off forever in that direction. We could keep going out, and we'd see that it just keeps going. But this is at the point 3, and I can do that with the graph trace menu, trace, graph trace, switch to that one, and if I just slide over to here, I should be able to, I see that 3, 0 is that point right there, and that's the lowest value of x that exists, but it goes on forever the other way. So, quick recap. The 3 situations we look for to limit domain. 1, the graph of the function. If the graph has a hole, if the graph starts or stops, if the graph has a maximum or minimum, then we use that. Number 2, we're not allowed to divide by 0, so we set the denominator equal to 0, we solve for what that value is, and then we say that x cannot be that value. And finally, if we ever try to take a square root of a negative number, we set the radicand greater than or equal to 0, and then we solve. I think if you play around with these problems, the must-dos, and I would suggest that if you want to get something higher than a 4 or a 5, try some of the aspire to-dos. That way you are set on this. So I'm going to say just get to work on that, and I will talk to you all later. Bye-bye.